Hi everyone, this is Kiran Rawat, and I have been learning linear algebra. And the today's topic that I have learned was linear transformations. So when we are talking about the transformation, to transformation is nothing. When we are giving input to this transformation, it will give you some output. So we call it linear transformation. Let's say if I have vector this one, so it will give you basically it will change the position of this vector, right? So it get transformed. So this is we call transformation. And in this linear transformation we need to understand when we are talking about the transformation. So linear transformation means basically the grid line is not going to change ever. It is not going to be curvy at all. So we call it linear transformation, and the origin is always going to be fixed at 0 comma 0. That is the coordinate of that point, right? So yeah, so this was the linear transformation. Okay. So when we are talking about the linear transformation, so this is like the visual representation what I have learned today. So for example, if I have this identity matrix, let's say, yeah, so these vectors are always called basis vector, as we all know. And basis vector, basically when we are scaling up the basis vector, then only it get transformed. So every single vector, the other than the basic basis vector, is the combination of these basis vectors. Right, for let's say if I am increasing the value for the ith term over here, so you can see the exit distance is being expanded over here, right? In the negative value, it is going to it is going to be flipped over here, right? When we are talking about the gth value, you can see that yth distance is getting expanded. Okay, what about this value? When we are changing b value, like this coordinate is 1 comma 0, right? So when we are changing 0 to any other value, you can see that it is going to share it up towards the x. Basically the y jth vector is going to be dependent over your x vector position. And same as for the c, it is going to be shared up towards the y y direction. And basically share is nothing but when two vectors are getting dependent on each other, we call it share it up. Okay, rotation and scaling up, scale, I already told you. Rotation is something when we are just flipping the paper. For example, we have a like we have a page, and when as we can see over here, the ith vector is always going to be to the right of the jth vector. So whenever you are seeing any vector where I is going to be over here in the left direction, so basically you flipped the paper, right? So you can understand like it. So yeah, so this today I have learned. So I made this with the help of Claude AI. So we can have the basic understanding. So when we are talking about the matrices, what matrices is doing? Matrices is doing nothing, but it is manipulating the vector space. And when we are talking about this, we need to understand not only this basis vector is getting changed, but every other vector is also getting changed over here. And that's why your whole space is getting changed. So vector space is getting changed because the position of vectors are getting changed. Okay. So yeah, so this was the idea of the linear transformation. So it takes every vector and moves to a new place. What about the determinant over here? Because whenever we are studying determinant in our 12th book, it basically gives you the formula how you can calculate. But what actually it means, determinants tell you how much transformation scales area. So when we have this basis vector, so the area of the square metric, like square over here, is unit 1. Okay, but what if I am going to scale it up, like 2 ith factor to 2 and jth factor to 2, then the area is going to be becomes for this square is 4, right? What I am saying, let's say this, and then the area of for this is going to be 4, right? So basically determinant tells you how much transforms scales the area. So yeah, when a determinant is basically less greater than 1, so it is going to be scale it up. But when it is less than 1, so what does that mean? So you can see the orange parallelogram, 4x is smaller than means space shrink. So basically it is getting squeezed, right? If it is equals to 0, so every single vector is going to be in a line. So every single point, basically vector is nothing but you can represent at like a point in a vector space. When we are talking about the coordinate space, so we can have coordinates for every single point, right? So it is a vector only. So yeah, so the entire 2D space collapse onto a single line. If it is 2D, it is going to be collapsed into 1D space. If it is 3D, it is going to be collapsed into 2D space. Okay. And this transformation is irreversible and it's very simple when we have the determinant 0. So basically, if I'm going to, that's why we are not having any inverse for non-square matrix. And for the matrix which is non-singular, because when we have the determinant 0, so uh, so basically your dimensions are getting changed over here, and when the dimensions are getting changed, what it means that you have new information or you could lose the information, so you are never going to get back to the original position of any vector. And that's why when we talk about the matrices and the determinant, we always know that if determinant equals to 0, so we can't have any inverse for that matrix, right? Okay, so this is the inverse. You can see the purple area is the position for the actual vector, and this red area basically is the position of your changed vector. So when we want to decrypt the data, uh, what encrypts once, so we need to have the inverse. Okay. Non-singular, I actually mistakenly said non-singular. That is non-singular. No, that is like determinant 0, so that is going to be singular matrix. Okay, so for the singular matrix we are not going to have any inverse. So basically it is going to be invertible, right? Okay, so for the non-square matrices, we do have the inverse, but that we call it a pseudo inverse in mathematics. Yeah, regular inverse does not exist for not pseudo inverse we call it. And that gives you the best possible approximation. Basically, when we are talking about the inverse solution, so every single vector we are going to have the like the unique value of the x for that particular vector when it is getting changed. But in this non-square matrix, we don't have any unique values, and that's why we call it pseudo inverse. We are just making guesses over here. Okay, so yeah, so that's all that I have learned today. So I'm going to share the link in the description, so you can just go over here and you can make some basic understanding about the matrices. Okay, yeah.